I'm Christopher Marsh. I'm a postdoctoral fellow at the University of Saskatchewan, and then my co-conveners are Philip Harder, research associate at the University of Saskatchewan, and Vincent Dionne at Environment and Climate Change Canada. So just a reminder that this is a recorded seminar. If everybody could just keep your microphones muted, please. Then during the question and answer, you can either type it in the chat, or you can unmute yourself to ask. I'm gonna give about 13 minutes for the speakers. I might just unmute myself and just verbally say, time's up if you're not quite there at 13 minutes, and then we'll have a couple minutes for chat. So let's get started. So our first speaker is Camille. Please take it away.
How's that?
Looks great, thank you.
Perfect. Okay, so I'd like to talk to you about a recent study we did. The goal was to improve the snow analyses that ECCC produce for hydrological forecasts. So my work is a work of multiple people, Vincent Dionne, Etienne Gabory, Vincent Fortin, and other teammates. Sorry. All right, so let me give you a bit of context. ECCC recently designed and implemented the National Surface and River Prediction System, what we call NSRPS, and it's to provide surface and river flow analysis and forecast products across Canada. And you have here a simplified diagram of what NSRPS looks like. And within NSRPS, you have the Canadian Land Data Simulation System, what we call CADAS. It produces snow analyses, and these are used to initialize the land surface model, as well as their routing component, the HPS. And then the land surface model that we use to model the snowpack is SVS, what we call soil, vegetation, and snow. What our issue was that originally CADAS was designed to improve atmospheric forecasts with less focus on hydrological processes. So what we had until recently was an assimilation method developed by Bruce Brasnet, the OI, optimal interpolation. We assimilated in-situ snow depth data from SYNAP, SWAB, and METAR networks, and the frequency was every 6 hours when the data was available. On this map here, you can see the position of these three networks combined across our study domain, so which covers most of Canada and then northern parts of the United States. The problem is that when snow data assimilation occurs, the related increments tend to remove water from the system. It can happen throughout the snow season and up to 4 times a day. And the problem is most important during the snowmelt period, because this lack of water conservation is really problematic for streamflow forecasting. And we expect something like that, spring freshet, and this is what we get instead. In graphic mode, you have, this is a discharge at an observing station on the Ottawa River. In black are the observations, and in red are a streamflow forecast that use snow analyses as inputs. And when you have no data simulation, so they're really snow modeling more than snow analyses, this is what we get. If we assimilate in situ snow depth data, this is what we get. As you can see, the assimilation process removed water from the system, and our spring freshet is underestimated quite largely. So hydrologists decided to use the simulated snow data without data assimilation until a solution was found. And this is where our research comes in. So we tried to find a new data assimilation method that would solve the problem quite quickly. So instead of assimilating in situ snow depth observation, we replaced the data assimilation of in situ data by IMS snow cover extent, and based on what was done at that moment at ECMWF. So this is what happens if the model and IMS data gives snow-free conditions. We simulated 0 centimeters. If they disagree, but IMS gives a snow-free condition, we simulate a 0 centimeter snow depth. If both agree with snow on the ground, we don't have any data assimilation occurring. And if they disagree, but IMS gives snow on the ground, then we assimilate a 5 centimeter snow depth. We don't assimilate anything in mountainous regions based on what ECMWF was doing at that time. And during this process, we found that there was a large precipitation bias in mountainous regions, and we fixed that one through debiasing of the snowpack depth. So this is the experimental setup. Our domain is portrayed here with the mountain mask that we use in pink. So we don't assimilate anything in these areas. So our runs go from September 2018 to June 2019 at a 2.5 kilometer resolution. We force our model with the high resolution deterministic prediction system from ECCC, and we use CAPA, the Canadian Precipitation Analysis, for precipitation. What the ECMWF does to mask out mountains, it uses simple 1,500 meter threshold of altitude. We looked into a different way of doing it, and we use a mountain mask based from a study from Karagule et al. In 2017, and it defines mountainous regions based on slope, local relief, and profile type. And this is what is portrayed by the pinkish area in this figure. So we ran 3 simulations in CalDAS control. It's really an open loop. There's no data simulation. In CalDAS ref, it's what we had before, the old analysis. So there is data simulation. We simulate in situ snow depth with an OI, but in this case, it's the same in the 2 runs. The simulation frequency is a 6-hour. We don't have any debiasing in mountainous regions to counter the precipitation bias in these regions. And then we do assimilate data in mountainous regions. Now, the new analysis, what we have is we simulate a snow depth derived from IMS data. We haven't changed the assimilation method at that point. The frequency is 24 hours frequency, simply because IMS data is only available once a day. We have the SD debiasing in mountainous regions, but we don't simulate anything in these regions. So let's start with the evaluation of snow depth. First, we base this evaluation against the in situ snow depth data that is used in CalDAS ref. So you won't see CalDAS ref in these figure here because it would be too incestuous. So you have CalDAS control in gray and CalDAS IMS in yellow. First box is bias, standard deviation of the error, and then just the number of observations that we use to produce these figures. And what we see is that CalDAS IMS improves the bias by decreasing the negative bias that we see in CalDAS control. And it has a very neutral effect on the standard deviation of the error. So this bias being improved throughout the year, throughout the domain, is a very positive point. Then we evaluate snow depth against the CAN-SWE data set. So independent data over multiple regions. And first, let's look at the greenish region here. It's Alaska and Antarctic. And what we see, so we have three curves, CalDAS control in gray again, CalDAS AMS in yellow, CalDAS ref is in blue this time. In these regions where snow covers the ground most of the time, there is no data assimilation in CalDAS AMS because if both agree, the model and AMS, nothing is assimilated. So we rely heavily on the snow model. And in this case, being an Arctic region, our snow model is not performing as best as we hoped. But we've all encountered problems in the Arctic with respect to snow modeling in this case. And you can see that the use of in-situ snow depth in this case is helpful. In mountainous regions, so the blue region here, Western US, there is very little assimilation once again, because we are looking at mountainous regions. And in this case, it is helpful. We're close to CalDAS control, but we're better than the old analysis. Let's look at two other regions. Western Canada, so very mountainous region again. We rely heavily on the model, and in this case again, it's a positive thing compared to the old analysis. And then in a non-mountainous region, the purple one, Eastern Canada, here is where the assimilation of IMS data helps the most because it really corrects the snow line in this case, and we're even better than CalDAS control and CalDAS ref. So now let's look at the impact on hydrology. Here I'm only showing one observing station, again the Ottawa River station in red, portrayed in red here, and then it's a watershed in green. It's in Eastern Canada. The first graph here shows you the water storage in the snowpack down there and then in the soil up there for the three simulations. You can see that in CalDAS ref, we start with a deeper snowpack than the other two simulations. However, if you look here, the cumulated runoff, you can see that you have less runoff in CalDAS ref than in the other two simulations. Why? Again, we go back to the fact that we have negative increments in CalDAS ref, and if you look here, the water mass balance, if we have a perfect water conservation, we stick to the zero line. However, in CalDAS ref, you can see that we're losing a lot of water when the snowpack is melting. And that's because the negative increments just remove water from the system. In CalDAS IMS, however, the yellow line, you can see that we're pretty close to the zero line and to CalDAS control in gray. So this is a very good thing. Starting when the snowpack is completely melted, you can see that the water mass balance that takes into account the moisture in the soil is being modified by the assimilation of CMOS and SMAP data in this case. So these two curves are really parallel because it's the same, they're affected by the same data assimilation. So we have in CalDAS AMS compared to CalDAS ref, we have increased runoff and a much improved water balance, so conservation. And if we go back to, you've already seen these two figures.
Sorry, just if you could start to wrap it up.
Yeah, it's my last slide before the conclusion, so we're good. So this is CalDAS control, as we've seen before, the observations in black and the discharge forecast in red. What we have output with CalDAS ref, so we saw that we were missing lots of water, and now with CalDAS IMS, we see that we solve this problem of water conservation quite well. So in conclusions, the new snow data assimilation method brings an overall improvement to snow analysis substantially enhances water conservation, which is reflected in the generally improved stream flow simulations, but it does rely heavily on the snow model, in this case, the SBS. So we see its flaws in areas like the Arctic. This work is a first step towards a new snowy data simulation process in CADAS, and the final objective is to produce a reliable snow analysis to initialize and improve NWP models, as well as environmental prediction, including flood and drought forecasts. And I'm done.
Awesome, thank you so much.
You're welcome.
There is a question in the chat for you, perhaps, just because we are on time for our next speaker, perhaps if you could just address that in the chat.
Yes, perfect, I'll do that.
And then we can just kind of do that and then keep on with our next speaker. So I'd like to welcome Vasana to the floor. Looks great.
So today I'm presenting about assessing the spatial distribution of the snow depth in different environments using unmanned aerial vehicles LiDAR. As many of you might already aware, the spatial variability of the snow cover depends on different factors, such as the variability of the topography, the variability of the vegetation types and density, as well as the variability of different meteorological factors, such as exposure to wind, precipitation, and solar radiation. Accounting for this variability of the snow cover is important in accurate flood forecasting, as well as to have proper water resourcement management plans. The main objective of our study was to examine and better understand the small-scale snow depth variability in open versus forested environments by using UAV LiDAR data. At the end of this study, we will be answering two research questions. First one being, how does the snow accumulation and scaling characteristics vary between and within open fields and forested environments? And the second one is, what are the relationships between snow depth, topography, and vegetation structures? Our study area is mainly focused on Eastern Canada in Southern Quebec. We selected 3 study sites that represents the main land use types in this area. Saint Martin and Saint Maurice areas are 2 paired agricultural and forest patches. These are commonly called as agroforested landscapes in Eastern Canada. These 2 are located in the lowlands of the St. Lawrence River. And another site we selected, which is in Montmorency, which is in boreal forested environments. Compared to the 2 agroforested sites, Montmorency experiences colder temperatures, higher snowfall, and have a longer winter season. We carried out 2 LiDAR surveys, one in spring, another one in winter, to scan the surfaces to get the snow depth data. We used Metric 600 drone equipped with the Velodyne VLP16 LiDAR sensor to do our LiDAR survey. As well, we deployed a base station simultaneously operating with the LiDAR flights to differentially correct the data we collect from the LiDAR system at a later stage. Additionally, we carried out manual snow depth measurement campaigns in winter to validate the snow depth data we collected from the LiDAR system. Moving on to data processing and analysis, we first process the road trajectory data that we collect from the LiDAR system together with the raw base station data to get a corrected post-process trajectory file. And then we process this with the raw laser data to get a georeference point cloud. Then we classified this georeference points cloud to bare surface point. So in spring survey, we get the ground surface, and for the winter survey, we get the snow surface from this bare surface point cloud classification. Then we created 2 digital elevation models, one for the snow off surface, another one for the snow on surface. The difference between these 2 would give us the snow depth raster. As I mentioned before, we used manual snow depth measurements to validate these snow depth products. As well, we used omnidirectional variogram analysis to assess the spatial correlation and the spatial continuity of our snow depth data. We also produced some rasters, like variables that represents the topographical features as well as the vegetation characteristics in our sites. And together, we used a random forest regression model to investigate the relationship between snow depth with these topographical and vegetation characteristics of each of our sites. Moving on to results, these are the snow depth maps we derived from our collected LiDAR data from our system. At a glance, you would see on average the open field areas accumulate more snow than the adjacent forested areas in all three sites. And the small scale variability of the snow erosion and snow accumulation patterns is also well captured by UAV LiDAR, especially in these two agroforested sites, Saint Mark and Saint Maurice. The highest snow accumulation was observed in narrower canals as well as the forest edges. And in Montmorency, the highest snow accumulation was observed in forest gaps in the boreal forested environment. And compared to the two agroforested sites, we see more data gaps in the boreal environment. It's because of the presence of the very thick canopy cover in this site. Validation of our snow depth data with the manual snow depth data shows that the LiDAR was able to produce snow depth values less than with an RMSE less than 0.16 meters in the open areas with the presence of a basal ice layer, and in the forested environments with an RMSE less than 0.19 meters with different canopy covers, which is in accordance with the previous efforts with UAV LiDAR. The spatial correlation analysis with the variogram analysis shows in all the forested environments, the semivariance is higher. That means the higher spatial variability of the snow cover is observed in all the forested environments, the highest being in the boreal environment in Montmorency. As well, these three forested environments show scale break distances less than 10 meters, which is in accordance with the previous studies, previous values reported by the airborne laser LiDAR surveys in similar environments in alpine environment. Compared to the forested areas, the field area shows scale invariance behavior like in Saint Mark, or a larger scale break distance like in Saint Maurice, which is similar to the previous efforts. This is mainly associated with the higher wind speed experiences by these two sites as confirmed by the wind rose plots collected in these two sites. Compared to these two agroforested sites, Montmorency field area shows a smaller scale break distance. This is mainly because of the smaller extent of this area as well as the sheltering of the wind of this site. Next, the relationship of snow depth with the topographical and vegetation indices. So we used a random forest model to investigate this relationship. This relative important plot shows how much including a variable could improve the accuracy of the model and vice versa. For the random forest model, we used 7 variables at each site. 2 variables that represents the forest edge effects because we identified the snow accumulation along the forest edges was significant in the agroforested environments. So we used windward forest edge proximity and north face forest edge proximity, and as 2 variables, we used topographic wind sheltering index, slope, and west-east aspect and south-north aspect. To represent the vegetation characteristics, we used a leaf area index. So as you can see, in Saint Mark and Saint Maurice, these 2 agroforested sites, when we observe the combined landscape, that means the forest plus the field area, the windward forest edge proximity has the highest influence for the snow depth variability of these sites, That means including this variable improves the model accuracy by 60 to 80%, whereas in boreal environment in Montmorency, leaf area index seems to be the highest influencing factor for the snow depth variability. But when we model this field and forested area independently, we see the order of the variables change to some extent. For instance, in SNMAT, in forested area, south-north aspect seems to have the highest influence on the forest snowpack, whereas in the field, it still seems to be the windward forest proximity, which indicates the different processors influencing the snow depth variability in field and forested areas. Now, moving on to conclusions, from our results, we observed the open field accumulate more snow than the deciduous environments. But when we discard the snow accumulation along the narrower canals as well as along the forest edges, the deciduous forested environment seems to accumulate slightly higher amount of snow than the adjacent open fields. And coniferous forest seems to accumulate more snow than the deciduous environments. This is mainly because the site receives more snowfall than the deciduous environments. And the adjacent open fields accumulate more snow than the coniferous forested environments. From the spatial analysis, spatial correlation analysis, we found the deciduous environment snowpack is more homogeneous, whereas the snowpack in the coniferous environment seems to be more spatially variable or heterogeneous and more spatially continuous. And the snowpack in the open field seems to have a prominent effect from snow redistribution due to the wind speed. As well, the forest edges and the forest gaps seems to accumulate more snow than all these environments. And our results confirm the previous findings from remote sensing data, such as the snow accumulation decreases with the increase of the canopy density, and the snow accumulation increases in the northerly oriented slopes in the northern hemisphere. When these landscapes are taken together, we found in agroforested sites, incorporating the wind-related forestage effects has improved the model accuracy by more than 50%, whereas in the coniferous environments, incorporating the forest structure variability improved the model accuracy by more than 60%, which implies that including and better representing these processes in process-based models is very important, as well as the prominent topographical features such as canals to accurate estimates of snowpack dynamics in these regions. Having said that, this also implies that having high resolution data is an added advantage, especially in modeling. So if you were to do a modeling or sampling in these areas, it's better to select a resolution well below the scale break distances we found in this study to have more representative spatial variability of the snowpack in your modeling. And finally, the finding of this study could be applied or extrapolated in similar landscape in southern Quebec, as well as any similar environment that addresses the relevant processes. With that, I would like to conclude my presentation. Thank you very much.
Excellent. Thank you very much for that. I'm wondering if we have any questions. I have a quick one for you. I'm just wondering how tall the vegetation in your open fields typically is.
In winter, they are agricultural fields, so
okay.
They normally like few centimeters of short shrubs.
Yeah,
Just
sure.
that. Yeah.
So they're quite profoundly impacted by blowing snow events then.
Yes,
yeah.
Very much.
Yeah. Oh, excellent. Well, thank you very much. We're on time here, so if there's no other questions, we'll move on to Nicholas. Take the stage. You're still muted, Nico.
Thank you. You can see my screen?
I can, thanks. Looks good.
Okay, thank you. So I'm Nicolas Roux. I'm a postdoc at the University of Quebec in Montreal. And today I'm going to talk about the research we're conducting there on estimating precipitation phase at the surface and how that can impact snowpack evolution in a site in Eastern Canada. Some background. So as we know, we have a wide choice of different phase partitioning methods that can be used in models. And we know that those methods mainly differ in their abilities to estimate precipitation phase around 0 degrees. And this can significantly impact snow accumulation and snow melt. So this research is part of the SAJESS field campaign that aimed to investigate the processes associated with the variability of precipitation during cold season storms in the Central River Basin. So the goal of my presentation right now is to first evaluate different PPMs, so phase partitioning methods, using observations of precipitation phase at the surface, as well as to assess the impact of the different PPMs, compaction and snowfall density schemes on simulated snowpack accumulation. So first, I'll introduce SAJESS and the data we're using here. So SAJESS took place in Eastern Canada in Northwest New Brunswick in Edmundston, and took place between December 1st, 2020 and April 30th, 2021. And we collected 1 minute data during SAJESS, and in this research, we're also using 1 hour data from a nearby ECCC station that was approximately 100 meters from our main station. And so within the data we're using, we're using optical laser disdrometer data, as well as macro rain radar data. I'm going to go back to that just a bit later. And to drive the model, we're using air temperature and humidity, as well as 10-meter wind speed, incoming shortwave and longwave radiation, accumulated precipitation. And to evaluate the model, we are using snow depth from 3 different sensors. So for those who are not familiar with what's a disdrometer and macro rain radar, I'm going to introduce those here. So here's a picture of a disdrometer. Here we're using the Parsival 2. And the disdrometer measures particle diameter and fall speed, and also gives us the precipitation type via some weather codes. So this is pretty neat for our research right now. And the macro rain radar measures the vertical profiles of reflectivity, Doppler velocity, and spectral width. And we are using those within an algorithm that has been published to estimate the vertical profiles of precipitation type. So I'm using 6 different phase partitioning methods. So those methods estimate a liquid fraction between 0, which is snow, and 1, which is fully wet or liquid precipitation. So some of the methods we're using are the constant threshold in air temperature of 0.8 degrees. This threshold came from the study of Jennings et al. 2018 and was optimized for this region. We're using a linear regression between -2 and 2 degrees, a constant threshold in wet bulb temperature of 0 degrees. I'm using 2 parametric equations, the one of Harder and Pomeroy 2013 and the one of Wang et al. 2019, which are shown here. And finally, from the weather codes given by the Parsival, I could estimate an hourly liquid fraction. And finally, I'm using the CROCUS snowpack model, which is a multi-layer model, which we are running at 1 hour time step. And what we're looking at here in this study is the uncertainty on snow accumulation. And for that, we are looking at 3 different compaction schemes, which are, I'm not going to go into much details into the schemes. We can find them into the study of, into the manuscript of Lafayette et al. 2017. But mainly those B92 and T11 differs into estimating the snow viscosity, and S14 estimate snow compaction using a specific surface area for the first 48 hours of snow accumulation. And we're also using different snowfall density schemes. Here I can introduce them quickly. We have V12, which estimates a snowfall density based on temperature and wind speed. SO2, which also uses air temperature and wind speed, as well as relative humidity. And we have a very simple method, A76, which is only based on air temperature. And we can see how they differ into estimating snowfall density. And also in the model, what we're using is the phase, the precipitation phase, so either snow and rain as an input, and that is part of the study using the PPMs to look at the uncertainty and snow accumulation. What I've put in bold, B92 and P12 are the default schemes in the model. So if I'm not mentioning a study on, or like an uncertainty on the schemes, on the compaction or density schemes, we're using those two models. So first I want to compare the different phase partitioning methods and how they represent precipitation at the surface. So I just took an example of an event that we observed early April 2021. And during this event, we can see that, so the first plot is the vertical profile of precipitation type estimated from the MRR. And the first half of the precipitation event was mainly snow, which is in blue like that. And the second half of the precipitation is mainly mixed precipitation and rain. And here I'm showing the time evolution of the liquid fraction based on the different PPMs. And what we can see is during the snow part of the event, only the particle, which is, the disdrometer liquid fraction, which is in black, estimated a liquid fraction close to 0 or equal to 0 during the snow event, and the other ones estimated a higher liquid fraction. And when the event turned into mixed precipitation, mainly the particle, or only the particle, picked up this new precipitation type and phase, and increased the liquid fraction up to 1, which is fully liquid precipitation. So this is just an example of one event. We have different events that we've analyzed, but the main conclusion is that the disdrometer is the best PPM, especially compared to the macro rain radar measurements. So now we can compare the performance of the different PPMs based on the disdrometer being the reference. So here I divided the estimated liquid fractions into 3 different snow precipitation types, which are snow if the liquid fraction is below 0.1, rain, and mixed precipitation otherwise. And I'm using different metrics, the probability of detection, the false alarm ratio, the frequency bias, as well as HSS, which is here I'm using it as a global score to see which methods might perform best. Once again, using the disdrometer as a reference. And we can see that using the HSS, so the global score, that it's hard to find one method that performs better than the other ones, except for the linear regression that doesn't perform as well as the other ones. But what we can see is that using a constant threshold, either in air temperature or wet bulb temperature, obviously we cannot estimate mixed precipitation, but we have a good estimation on average of either snow or rain precipitation types with a high probability of detections. However, compared to the other methods here, we have also a higher false alarm ratio. And when it comes to estimating mixed precipitation, this is all the methods struggle compared to the Parseval. And what we can see is mainly we have the probability of detection is not very high for most methods except for LR, but we also have for all of the methods a high false alarm ratio, unfortunately, and only the method of Wang et al. Had a bias closer to 1. So from that, we can estimate that maybe Wang et al. On average estimates better all the precipitation types. And so now I'm moving to the Snowpack simulation. So here, I'm showing just one season because we only have data for one season. And in this yellow-green shaded area, this is the observation of snow depth from the 3 different sensors, and the lines represent the simulation of snowpack evolution using the different PPMs. And as we can see, mainly the methods are very close to each other for most of the accumulation area or the accumulation period, except for the method using the linear regression, which greatly underestimates snow accumulation. And during the spring, when we had more mixed precipitation and warmer temperatures, that's where we start seeing more differences in the accumulation, the snowpack accumulation simulations. So now what I've done, if I go back to this time, to this slide, we see all the gray shaded areas, which are the accumulation events. And here I'm just representing all the accumulation events one after the other. And in red, I'm showing all the events with what I call the warm events with air temperatures below -2 degrees. In this graph, what I'm showing is the accumulation the change of snow depth during those accumulation events. The bars are the mean snow depth accumulation, and each point is the simulated changes of snow depth from the different PPMs. And here I'm showing the event average liquid fraction from the different PPMs. So what we can see is for the warm events, or the red events, once again, we see that that's when most of the PPMs differ in estimating an average liquid fraction. And mainly this results in differences of snow depth accumulation during the warm events because of the different liquid fractions estimated. So now I'm gonna talk quick. I'm gonna show the performance of the different PPMs, the compaction and density, snowfall density schemes on. I just use one metric, which is the mean bias here of the simulated and observed snow depth changes in snow depth during the warm event. So it refers to the plot we just saw previously. And here I'm just showing for the reference case, how the different PPMs performed into simulating changes in snow depth during the warm events. And as we saw earlier, using LR, for example, the linear regression, we greatly underestimate the snow depth accumulation. And here, actually using the disdrometer data, so we saw that was the reference phase, doesn't give us the best results, but Wang et al. 2019 gives us the best bias in accumulated snow depth. And now we can play with the different snowfall density schemes here. And if I moved from this 12 to A72, this time for all the methods, we really, even less, we underestimate snow depth accumulations. And once again, what we notice is Wang 2019 gives the best bias. And now I played with the third snowfall density scheme, and this time compared to the reference scheme we use, we greatly overestimate snow depth accumulation. And this time, for the first time, the disdrometer data, the simulation using the disdrometer data gives the best result. And now we can play with the different compaction schemes. So this is once again the reference case. We see the same mean biases as this previous slide, or this previous row. And now we can play with the different another compaction scheme, T11, which, like I said, was close to B92, but just differs in estimating the viscosity of the snow, and the results are very, very similar. And once again, Wang 2019 gives the best results. And finally, if I move to the third compaction scheme, this time the results are way different. Or we are getting away from the observed change in snow depth. So to conclude, I just show that Wang et al., it was hard to determine that, but more closely represents the precipitation phase when it's estimated from the disdrometer. And that, unfortunately, in the simulations, using the disdrometer data to estimate the precipitation phase, which was the best precipitation phase estimation, didn't give us the best results in estimated snow depth. And Wang et al. Using the simulation with Wang et al. 2019, best estimated the changes in snow depth. So some future work we're going to do is this time quantifying and comparing the sensitivity of the different PPMs, compaction, and snowfall density schemes. So here are a few the references. Thank you.
Excellent. Thank you very much, Nico. So we actually have a 10-minute gap until our next presentation. So because there are no posters associated with this session, I'd like to invite anybody to ask some questions on the previous three. I know there's been some conversations in the chat, but I'm wondering if there were any other questions that anybody wanted to raise. Certainly, let's start with any questions for Nico, and then we can kind of open up to more global. So are there any questions for Nico?
Can I ask a question?
You may, yes, of course.
Hi, Nico. I enjoyed your talk.
Thanks, Philippe.
I'm not at all biased in where I'm coming from when I ask this question. But preset phase is obviously something that's captured my attention in the past. I'm just wondering about like applying this work in other places. So the one aspect of, this work is all in New Brunswick, which tends to be more humid climate? Is there any prospect of doing it in a more arid or drier climate? Because the one thing that I found in my work was that sort of the general humidity of your region will kind of determine which of your phase methods will be better than others. So methods that account for humidity will do better in drier climates because it accounts for that dynamic a bit more. So anyways, long story short, any chance of this could be applied in drier places to see if some of these patterns hold?
Yeah, that's a good point. Yeah, I think, like you said, it's biased in this study because it's a more humid area. And like, for example, Harder and Pomeroy, your method was developed in a more drier mountainous area, so it's not really applicable. I think it's a good point. The nice thing with this study is that we had a parsible to estimate the precipitation at the surface. And even just being able to drive the model with that was kind of nice to have the best precipitation phase. But I know we have a few more parsibles in the Rockies, so maybe we could extend this study to like the Canadian Rockies and use the data there for a few years as well. Yeah.
Thanks. I found it quite interesting that your parsible at times is not actually your best input even.
Oh no, that's a bit
frustrating. It's fascinating. Yeah, thanks.
Thanks.
So I have a bit of a follow-up with that, just because I'm not super familiar with determining the phase from those instruments. Are there any issues with high wind speeds and the fall velocities of mixed phase being a bit different? Does that have to be taken into account, or how do you deal with that?
I didn't directly took that into account because initially we tried to determine the precipitation phase and then the liquid fraction based on just the force speed and diameter of the particles. And then that didn't work very well, most likely because of wind speed issues, or parts of it, and also the uncertainties in the empirical equations we could use to estimate the phases. So that's why we moved to the weather codes, which seem to work way better than estimating the precipitation phase with the force speed, for example. So I didn't see any issues. Like, I was really impressed by how accurate the precipitation phase or the precipitation type was estimated by the weather codes. Because it also includes, it's kind of a black box from what I understood, but it uses force speed as well as the precipitation rate to determine the precipitation type. I don't know exactly how, but I was impressed by how well it performed. But yeah, wind speed is definitely could be an issue in determining for precipitation force speed or particle force speed.
Gotcha. Excellent. Thank you. Are there any other questions for any of our speakers? Yeah, go ahead.
Can I ask to the Asana? Actually, it's kind of the value on the chat is the R-square value from the random forest model, because based on that is delta I, that the R-square value is not too high. Actually, is my result also pretty similar range of that is with the same kind of analysis. So what do you think about is any kind of potential variable? Because there will be some missing variable, missing physical characteristic in the random forest model based on the accuracy. So do you expect is any kind of additional physical variable may impact on this that special structure of from these LiDAR snowdepths?
That could be. That also, like in random forest models, it usually gives the R-square for the validation data set. So we thought, like, if we have this type of values like 0.5 at least, that means it's working better. like for the linear models, you get the calibration R-square statistics. So it's like very high and all. But here, even like for the validation set, if you get like 0.5, 0.4, that means it's still better.
Okay.
But yeah, we were also thinking like if we miss something or that, but it doesn't seem so. So maybe it's something with the meteorological variables. But
yes. All right. So, oh yeah. So actually, my first kind of our approach is a more kind of is a soil and snow interaction and soil variable. Those may impact on the spatial pattern as well. So that is my kind of personal opinion. Would be helpful. And follow question is the boreal site and the agroforest site to have seems it's pretty different correlation. So why do you have any reason that makes this different? You expect?
You mean the performance of the model?
Yeah.
Well, in boreal forested sites, of course, even though we use LiDAR data, it's like you have a lot of data gaps. So we have deficiencies in that. But also the vegetation descriptors we used LAI for all 3 sites because we wanted to compare the 3 sites with the same variables. But like with random forest models, we first remove some variables due to the collinearity issues. So in the boreal forested environments, the LAI was not the variables that were selected for the initial runs. It was the gap fraction and the canopy cover. So those are the like most suitable variables. But we didn't use that because we wanted to have the same variables for all the 3 sites. Because LAI was chosen as a good variable for the agroforested sites. So probably if we use those 2 to represent the vegetation characteristics, the performance of the model might have improved a bit, but not so much. There are a lot of processes happening in boreal forested environments. And also the vegetation characteristics, there are a lot of things like the tree height and the canopy diameters and a lot of things in the boreal environment than the deciduous trees, I think.
All right. Thank you for your answer.
Thank you.
All right, we probably have time for one more question if anybody has a pressing question. Oh, all right. Well, perhaps we got about 2 minutes here. I just have a quick one for Camille then, with regards to the data simulation. You had noted using a mountain mask. I was wondering if there's any special treatment for the boreal forest regions and how you were ingesting the IMS data.
No, we didn't treat it differently than any other vegetation types. Obviously, it comes with uncertainties, but it wasn't considered at that point. We trust IMS data.
Fair enough. Yes, fair enough. It's kind of what that was the impression I got. I just wanted to make sure I fully understood.
Yeah.
All right, excellent. Well, I'd like to invite Lawrence up as our next speaker. And then this would be a really nice conversation we've had with everybody. So just perhaps if people wanted at the end of the next 3 presentations, we could just stick around for a few more questions so everybody has a chance to have questions asked of the next 3. That'd be really nice. But otherwise, Lawrence, the floor is yours. Yeah, looks good. Sorry, Lawrence, you're so many.
No, sorry, I had to find the unmute button when the screen changes. Okay, thanks for attending my presentation, everyone. Today I'm talking about how snow and permafrost are simulated in a new land model intercomparison project that's part of CMIPS 6. And how they compare to the standard historical simulations. And so this is work that's done in tandem with Eleanor Burke at the Met Office Hadley Center. and Gerhard Krinner at IGE in Grenoble, France, with additional contributions from Nathan Collier, Chris Dirksen, and David Lawrence. So the new tool I'm using in this work is a suite of simulations that are part of LS3MIP, the Land Surface, Snow, and Soil Moisture Model Intercomparison Project. This is a suite of simulations that are a sub-project of CMIPS-6, and they were developed with the goal of identifying systematic biases in the land components of the CMIPS-6 climate models, as well as evaluating feedbacks associated with snow and soil moisture. There are complementary projects that focus on vegetation and terrestrial carbon cycles, as well as land management. But this LS3MIP is focusing on snow and soil moisture. That said, central to all three projects is a baseline set of historical simulations that are called LandHist. That's their experiment name, whereby participating modeling centers run their land surface models in an offline mode. So they use the same configuration for their land model as in the standard historical simulations, but instead of coupling it to its corresponding ocean and atmospheric model, each land model is driven by an identical set of forcing data that was produced to resemble our actual historical climate trajectory. So this then provides us with a hierarchy of three ensembles that we can examine. We have this LandHist experiment ensemble that I just mentioned, where each model sees the same ocean and atmospheric conditions, but differences amongst the land surface models will drive differences in the land output. So structural or parameterization differences, for example. In the AMIP experiment, by comparison, each model sees the same ocean conditions, but there are different atmospheric trajectories that are possible, and those can drive differences in the land output as well. And then in the standard CMIPS-6 historical experiment, all three components evolve in a fully coupled manner. The only coherent forcing amongst them is historical radiative emissions. So for today in this presentation, I'm actually just going to focus on the LandHist experiment compared to the standard historical experiment. I'll refer to the first as LandHist and the standard experiment as the coupled experiment to hopefully avoid a bit of confusion. And I'm also only going to focus on analysis pertaining to permafrost extent and snow water equivalent, or sometimes it's integrated measure snow mass. So the models that I've listed here have contributed at least one LandHist realization, and generally speaking, they've provided sufficient variables of interest for the analysis. You can see that there's a few models that only contribute to permafrost or snow, but in general, there's enough data. So ideally, to validate these simulations and for comparison, we would want to compare the simulated snow mass and permafrost from the model ensembles with a hemispheric network of in situ measurements, what many people, I imagine, in this room would think of as real observations. But for both snow mass and permafrost, these sorts of measurements are too sparse in both space and time to be truly useful for comparing with the coarse scale output of climate models. So what we have to rely on instead are gridded observation-based data sets, which are themselves constructions. And in many cases, these gridded products are output from a model forced by historical estimates of important driving variables like temperature and precipitation. So in essence, they're very similar to the LandHist simulations themselves. At present, I would say this is simply an unavoidable compromise. When analyzing snow cover, we do have some further information available from visible satellite data. And for snow mass or SWE, we do have a family of products that assimilates both passive microwave satellite observations along with point snow depth measurements to produce its estimates. So there's a little more constrained output there. But I want to start off the results with two key conclusions from the analysis that we've performed so far. So the first is that for both snow and permafrost, there's better representation of the trends and historical variability in the LandHist simulations than in the fully coupled ensemble. We can see this here in the graph on the right, where it's showing for permafrost extent loss rate. The LandHist only simulations shown in the pink line are 9 out of 10 models are those loss rates are closer to the CCI permafrost, this is the so-called observational estimate, than the coupled model trends. Likewise for snow, I'm showing the correlation, month-by-month correlation of snow mass with the observations. And again, we see that for the LANTIS simulations, there's very high correlations. For the coupled model simulations, there's much lower correlations. This, of course, isn't a surprise, given that the LANTIS runs are driven by conditions representing our historical climate trajectory, but it functions as a bit of a sanity check. And it was useful to discover a set of runs from one modeling center that had been labeled as part of the LANTIS experiment, but which were in fact independent climate trajectories. So despite that point that we see better representation of trends and historical variability for both variables, there's still residual structural or parametrization errors in both variables. So this is my other big take-home message. In the case of permafrost, again shown on the right, there's no clear improvement in the LANTIS runs relative to the coupled runs now for climatological permafrost extent. And this is despite an improvement that I'm not showing explicitly in the representation of the number of climatological thawing and freezing days. So essentially what's forcing the permafrost extent you would expect has been improved, but the actual permafrost extent itself is not improved in the LANTIS simulations. For snow, I'm showing results from the coupled simulations on the two plots, the plot on the left for the coupled simulation and the right-hand plot beside it for the LANTIS simulations. It's split up into non-alpine and alpine snow. For alpine snow, we do see an improvement in the representation of alpine snow mass. The spread is reduced in the LANTIS ensemble, and the ensemble mean snow mass is close to the observational based estimates shown with those vertical bars. However, while there is reduced spread of non-alpine snow in the LANTIS ensemble relative to the coupled simulations, the ensemble mean is systematically worse. So you can see that the ensemble mean has increased relative to the coupled simulations. In particular, I guess if you focus on March, there's snow mass estimates from GlobeSnow 3 that are shown by the plus signs that are based on bias corrected GlobeSnow measurements, bias corrected with a suite of snow courses across the Northern Hemisphere. And so that also is systematically worse, the LANTIS runs with respect to that. Despite that, let's take a closer look at the spatial structure of the climatological differences in SWE between the coupled and historically forced LANTIS ensembles. So for these next few figures, I'm going to kind of switch around my comparison. I'm going to compare differences in snow water extent between the two ensembles, but they're going to be all presented as the coupled simulations minus the LANTIS differences, all for March. Looking at the median behavior of the models, we see that in alpine regions, the coupled runs generally have more SWE than in the LANTIS runs. So just kind of looking across the mountainous regions in Eurasia and North America, there's mostly red that you see. In contrast, in non-alpine regions, the coupled runs generally have less SWE than in the LANTIS runs. So mostly blue regions, we mostly see blue in the non-alpine regions. And we can link these differences to the amount, we can link these differences in the amount of snow to differences in how much accumulation via snowfall versus how much is due to ablative processes or differences in the ablative processes. So that's what I'm showing here. Again, across alpine regions, the increased SWE in the coupled runs is primarily due to increased snowfall. You can see that by comparing the center and the right-hand plot. So the increases in SWE in the coupled runs are primarily due to that increased accumulation in the coupled runs relative to their LANTIS counterparts, whereas across non-alpine regions, the coupled simulations have more SWE loss due to ablation than their LANTIS counterparts. So that was for the ensemble mean, ensemble median differences. We can also look on a model by model basis where instead of showing spatial maps, I'm summing up the regional differences. And the same conclusions hold for almost all individual models that we've examined so far. So I'm illustrating this on these plots where the relative difference in snow mass on the vertical axis is shown for each analyzed model on the horizontal axis. Model by model contributions to differences in accumulated snowfall are shown in the blue lines, and contributions from ablation are shown in red, with the net difference in black. And looking across the three plots at the blue lines, we see that for all models, the contribution due to differences in accumulated snowfall is positive, indicating increased snowfall accumulation in the coupled simulations compared to landhist. This is particularly true across alpine regions shown on the rightmost plot, where the accumulation, snowfall accumulation is between 50 and 150% higher in the coupled runs. In contrast, the contribution from ablation indicates that there's increased ablation, which is resulting in less snow mass in the coupled simulations occurring across all regions and all models. And so it's the net effect of these two contributions that differs depending on whether you're looking at alpine or non-alpine regions. In alpine regions, the additional snowfall accumulation in the coupled runs results in more snow mass in most models. There's two exceptions. In non-alpine regions, the contribution from increased ablation is stronger, and the net effect leads to less snow mass in the coupled runs compared to the landhist simulations. And so while the net effect between accumulation and ablation might result in reasonable Northern Hemisphere snow loss totals in the coupled runs, overall, it might be for the wrong reasons, given the disagreement that we see in the range of observation-based estimates over alpine snow, given the disagreement over non-alpine snow that we see in the landhist simulations. So another way of putting that is, when forced by historically accurate temperature and snowfall amounts, the climate models are producing too much snow mass. So to the extent that we trust the observations and the snowfall amounts that were used to force those landhist simulations, this discrepancy suggests that there could be too little ablation occurring in the snow season for the given temperatures. So just to conclude, as I said, for both snow and permafrost, there's better representation of trends and historical variability in the landhist simulations, but there's residual structural or parameterization errors in both variables. And in the case of snow mass, this residual climatological bias has three possible causes, two slightly boring ones, one saying that the forcing data might have too much snowfall in it, one saying that the observational estimates could of course still have errors in them, but also potentially that there are systematic model biases in the ablation rates for snow. And so that's sort of the state of the analysis so far. Some of the things that we're still exploring are the relationships between the ensemble mean trends amongst this hierarchy of ensembles I mentioned, as well as diagnosing possible links between snow insulation and permafrost biases. So thanks for your attention, and I'll take any questions.
Excellent. Thank you very much. Yeah, so are there any questions? There is one in the chat from Ed Kim. I'll just read it out. It says, very nice. If you could get new global SWE non-model observations, would your results suggest more benefit in non-alpine areas?
So would it be beneficial, I guess, to have a lot more measurements in non-alpine areas? I think that's certainly the more tightly constrained observational estimates so far, but of course, the observational estimates, the quote unquote observational estimates in alpine areas are really unconstrained. They're essentially, those are the ones that are basically just models. So yeah, for sure, of course, it would be beneficial to have better observations, real observations constraining the actual snow mass in alpine regions. Yeah.
Yeah, makes sense. Awesome. Well, thank you very much for that question. Thank you very much for the presentation. We'll move on to our next presentation. Alexandra, please, the floor is yours. And you're still muted.
Thank you.
Thank you so much.
You should be able to see the slides.
Looks great, thanks.
Thank you.
All right. Yeah, thanks for attending today. My name is Alexandra. I'm a student at U of T, PhD student under Paul Kushner. And today I'm going to be presenting my work using kind of this legacy temperature index model in a new light to look at reanalysis snow water equivalent and related snow variables. Yeah. Okay, so overall, we're all aware of the importance of snow and kind of its role in both hydrological applications and for the surface energy balance. It also insulates the soil, so it's kind of coupled to a lot of variables that are of interest. And there are, of course, these existing data sets for SWE, for snow depth, for snow cover that are either satellite-based or based on in situ measurements. But additionally, of course, there are products that are developed using snow models, either combined with observations or kind of standalone forced by something else. So the kind of remaining issues, and this kind of links to Lawrence's talk that he just gave, there are still some discrepancies among the data sets that come out from these models. And there's a lot of focus on the complexity and comparing parameterizations and decisions within the models. But it hasn't really led to identifying a best model. And in fact, what I'm sort of presenting here is a step back to actually look at some of the causes of the spread among, like I said, reanalysis snow products. So here are the kind of overview of the three data sets that I'm looking at. So from ECMWF, I have ERA 5, from the JMA, JRA 55, and from NASA, ERA 2. And what I am kind of getting across in this table is that there are snow model differences that are present, and these may give rise to differences in the modeled snow. Additionally, there are data assimilation differences. So just briefly, the first two data sets here make use both of in situ snow depth observations and a type of snow cover. And then they do a 2D optimal interpolation to assimilate those observations into the snow that's produced. On the other hand, MERA 2 doesn't do any land surface observation assimilation. So you can already see kind of differences there in terms of the source of data, the type of data, and the method that of assimilation that's done. And then there's a third factor, which I don't have here. And of course, that it comes back to biases in the variables that control the snow. So in the case of these models, it's typically temperature and precipitation that are kind of the main controls. And then there may be some role of humidity and wind that go into the snow modeling. So what we propose is to look at these forcing biases and try to separate them from the model differences and from the data assimilation related differences. Okay, so I'll just walk through kind of where this comes from. So on the two plots shown here, I'm showing the monthly precipitation. This is averaged over the 40-year period from 1980 to 2020, and it's a cumulative amount. And then on the right is the temperature, the monthly climatology for temperature. You can sort of think of how these control snow in that precipitation will be the kind of maximum, set the maximum for the amount of snow water equivalent that there can be. And then of course the temperature determines whether or not the precipitation is falling as rain or snow, and it can also impact melt, settling, densification processes, and so on. Okay, so going forward into the snow that comes out from the ERA 5 reanalysis, I'm showing the Northern Hemisphere snow mass climatology on the bottom left, and then just focusing in on December, January, and February, representing it as a time series on the right. So you see kind of all of these variables together. Now I'll add on the JRA precipitation and temperature, and you see that there seems to be more precipitation overall in JRA, and it's warmer, especially in the winter, than in ERA 5. But these two effects are, kind of in competition with one another. So it's not really clear how this will play out in terms of the total amount of snow until we look at the climatology here. So it seems that the precipitation bias results in this higher amount of total snow mass in JRA compared to ERA 5. But what's kind of quite different is when we look at the time series, there's a different pattern of variability. So there's kind of this decadal variation going on in the total northern hemisphere snow mass time series compared to ERA 5. And then finally, we'll add on MERA. So there aren't, very large differences in precipitation amount between ERA 5 and MERA 2. Maybe it's a little cooler in the winter, but again, there's more snow. So it's not really enough to look at these two variables on this average scale. We have to go back a little bit to kind of the distribution of biases locally. But here we have the snow mass, and actually, when we look at the time series, again, there's a difference in kind of the variability that's represented, and of course that average amount difference. So we want to know if we can identify or rule out some of the causes of spread in this climatological SWE amount, as well as find what's driving the different interannual variability across these data sets. And to do this, we use the simple snow model that I mentioned earlier, and it relies just on temperature and precipitation as inputs, and then generates snow outputs that we can analyze. Here's just a schematic of what I just said. As I mentioned, we're using precipitation and temperature, running the same model. So now we're kind of standardizing for the model physics, if you will. And what comes out are these reconstructed snow data sets. So what exactly comes out is snow depth and density, and then we can calculate SWE from there. Okay, here in a little bit more detail is the model. So this was developed at Environment and Climate Change Canada, kind of first in 1999 and then in 2003. These are the papers describing it originally. And I've recently updated it to be able to use it with all of these different inputs that I'm proposing, and also to update it so that it's in Python and kind of easier to use and share. So that will be released in the future. And kind of to walk through this flowchart, we have the inputs here on the left, so temperature and precipitation, with some amount just removed to account for sublimation and canopy interception. The rain is, the precipitation is partitioned into rain or snow depending on temperature. And right now it's just a very crude cutoff at 0 degrees Celsius. Based on temperature, the density of the new snow is determined. And then the depth comes out from those two other variables. That's combined with the existing snow at a grid cell. And then 3 processes are applied, and they affect either just the depth or the depth and density at the same time. And these are either precipitation based or temperature based. And everything is done with these kind of empirical formulations for these processes. So this model is, I'm so sorry, I don't know why it's skipping ahead. It's been used in a couple of different applications over the years. So it's been used as the background model for the snow depth analysis at CMC. And it has also provided some of the data for the yearly terrestrial snow update at the in the Arctic report card. So, all right, I've kind of walked through our methods. Now let's take a look at the resulting reconstructed data sets and what we can learn from them. Okay, so I'll remind you here that this is the total Northern Hemisphere snow mass climatology, multi-climatology, based on the native snow data sets. So that's ERA 5, JRA, and MERA 2 SWE. When we then combine that, when we then update that with the reconstructions, you will have seen that the peak snow mass has moved a little later in the year, and there's more snow overall. but the relative biases remain the same. So there was enough information in the temperature and precipitation to get kind of that ranking in the same order. And then what I'll do is, again, focus in on December, January, and February and show the mean in a bar plot and the interannual variability through the time series kind of separated. So the native data sets are the ones shown on in the cluster on the left, and then the reconstructed ones are shown with the black outline. So again, you see that the total snow mass is kind of well estimated with the reconstructions in this case, if you compare like the blue bars with the blue bar with the black outline and so on for the other colors. But what's striking is that when we look at the time series here on the right, the reconstructed data sets all are highly correlated over the 40-year period. So those are all shown in the dashed lines, and they're really overlapping pretty well over the 40-year period. What stands out again is the JRA native data set in the solid orange with its kind of decadal variations, and the ERA 5 data set, especially kind of around 2004. I have the correlation coefficients shown at the bottom among the native pairs. So they're fairly low, and then the reconstructed pairs, which are high across the board, and especially between the ERA 5 and JRA reconstructions. Okay, so that is kind of a first glance at how they all agree. When we take a look at different seasons and split regionally, so looking at the North American continent and the Eurasian continent separately, we can look at the reconstructions and the native data sets again and calculate the correlation coefficient, just as I did before. And now each black dot here is representing one of the three pairs, with the bar height showing the average. And what we can see is that for all seasons and for all pairs and for both continents, the correlation among the native data sets is low, and the correlation among the reconstructed data sets is high, and the spread is kind of smaller in those values. And so this again kind of leads us to conclude that any forcing biases that are present are not contributing to this disagreement that we see among the native data sets. Rather, it has more to do with the data assimilation technique and the potentially some model differences. Okay, so that's there. And then kind of a second approach that we took was to actually test what the effect of the forcing biases is and whether it can really explain the overall bias and kind of the amount of snow. This was done by generating monthly scaling factors based on the climatological values for precipitation, as I'm showing here, or for temperature. So basically, for each month, there's a value that takes, the original data set to the target, and that scaling factor is applied kind of on these sub-daily timescales, depending on which data set it is. What results
you
from
just had
this?
14 minutes, sorry.
Thank you. Sure. What results from this is adjusted temperature and precipitation, and we can use this to run the model again. We found that by doing this rescaling, we can improve the agreement between the reconstructed data sets. And so this kind of helps us estimate the role of the forcing bias in the overall snow bias in a kind of easy, straightforward way, rather than kind of rerunning the whole reanalysis system. So yeah, I'm aware of time. Basically, I just summarized what the rest of these figures show. Thanks all for your attention.
Excellent, thank you very much. Just wondering if we have any, like a super quick question? No, all right. Perfect. Well, thank you very much. And so then we will move on to our very last speaker. And I apologize profusely if I get your name wrong. But Joachim. All right, awesome. Yeah, I can see it. It looks great. Floor is yours. I cannot hear you. You're unmuted, but. I cannot. Yeah, no, I still can't hear you. Is Zoom set for the correct input? Oh,
is it coming through now?
I can hear you. Yes.
Okay.
Fantastic.
Technical little challenges. All right.
Thanks so much.
All right. Yeah. Thanks again for giving me the chance to talk today as the last summing is up. I'm Joachim Meyer. I'm at the University of Utah here in Salt Lake City, and this is work being done in conjunction with the National Weather Service here at NOAA and the USDA up in Boise, Idaho. And we're trying to test the operationally water forecasting ability of a physically based snow model and in a test basin here in the East River, Colorado. Motivation, I guess I'm preaching to the choir here a little bit, but just to highlight the few things that jumped out for us. Why we think this work is important is that our snow melt and timing magnitude has changed over the last couple of years. And this is also visible, for instance, here on the map on the right. This is the forecast for April 11th right here in 2022. And we see that throughout the region here in the upper Colorado Basin, we have different trends of the changing environment. And with the given methods that the Colorado Basin, the Forecast Center is using right now, it's getting more and more challenging to get these right. And the methods that the Forecast Center is working out now is a temperature index-based model. And these models have been shown that they can be directly correlated to forecasting errors if the calibration records that they're using are falling outside. The current year is falling outside of the past years. The model we will try to assess and evaluate here is the ice snowbell model. I'm going to give here a quick introduction for those who might not be familiar with it. It's a spatially distributed two-layer snow energy balance model. It was written by Danny Marks et al. In 1992 and 1999. Has since been extended by a team up in Boise, Idaho. And the basic workflow right now here is that you first set up the model domain, which I'm going to introduce in the next slide for East River. Then we collect the input data, which can be from points sources like some measurement stations, Snowfall network in the United States here, or other sources, or for instance, numerical weather prediction models, which we're going to use. Then this input data is distributed spatially by SMRF. So this is the module that's been written by the USDA folks to prepare the data. And then finally, we execute the model. All of this is in an open source fashion. So if you're interested in running yourself, you can go up and get it down from GitHub. And then also, like I said, this model has been extended to also run on high HPC, like high performance compute systems to utilize multiple cores. Our domain here is shown on the right-hand side. It's forecasted by, like I said, the Colorado Basin River Forecast Center. So if you hear me saying CBRC, that's what I'm referring to. And the way that they forecast this region is by dividing this region elevation band-wise into 3 hydrologic response units, so HRUs. The total test area is 1,370 square kilometers. We run it at 50 meters spatial resolution, and we ran it for the last 4 water years from 2018 to 2021. The comparison methods we had, or the comparison data sets we used, were the snowfall sites in site, which are shown here in the red little triangles. Then we also had the Airborne Snow Observatory, or ASO, surveyed that whole area with a LiDAR-based snow depth mapping. And then last but not least, there's also the USGS Stream Gauge, which is at the bottom here to measure or compare the output from the hydrograph. Input data that we use for this model is the the high resolution rapid refresh, or HRR model, which is the production model from NOAA since 2014. It's a numerical weather prediction model that runs at 3 kilometer resolution at the hourly scale of updates. So we can forecast up to 18 hours in advance. One of the outputs is shown here on the right. This is just a sample I took off last night from the weekend storm. And this is the forecast hour number 6, for instance. And this is, for instance, what we also use for the precipitation inputs, just to utilize more of the model physics versus the pure radar observation. Inputs we get from the HYR is air temperature, humidity, relative humidity, wind speeds, precipitation, and downward shortwave radiation. And these are then, like I said, fed into SMRF, spatially distributed for iSnowball to run. To give a quick info how I did this comparison. So you see point measurements are usually hard to exactly get right on the grid cell. So for those point measurements comparison, I used a spatial mean around this site, which is shown on top right. So this is the 2x2 square I'm using. And then also we this ASO coverage was not exactly overlapping with our domain. So we used kind of the union there. And then last but not least, we also compared the Snow 17 SWE data. So this is basically a model to model comparison, how the SWE from the index model fared with the SWE from the iSnowball. First off, let's look at the SNOTEL snow depth site. So now we're comparing a point measurement through time. And I'm just picking here 2 water years, which are kind of representative. 2018 was a kind of average, maybe a little below average, and 2019 was a high water year. And the first things that jump out for me, there's a kind of 2 different pictures we see. The first one is that the build up of the snow depth is pretty well. So up to peak snow depth in both of the years, independent of how much snow there was, it kind of follows fairly good well along. So iSnowball is the orange shaded area, and the SNOTEL sites are the blue solid lines. But once we get to the melt period, iSnowball falls kind of a little behind, melting the snow too slow, and also, which means too low of a melt rate, and also has longer presence of snow. So this is something you want to look into as a takeaway from this comparison, that we like the inputs from her, we get enough mass, but then when it comes to melted, we're kind of getting too slow or too far behind. If we do the spatial comparison, so now we also picked here just the 2019, because we had a flight that was early in the year before the melt, or kind of around the melt start, and then late when the melt was in full-fledged. We have a picture, kind of a spatial bias, if we think it is, or as something we want to look into if there's some spatially dependent melt that we also want to look into. Because you see up here in the higher elevations, like kind of the north and the east aspects jump out. When we looked at the precipitation input, they were all kind of similar. It was only the melt period that melted differently. So our takeaway from this here was that the lower elevations perform better than the higher ones. And then also the different magnitude and depth differences by aspect, like I said before. Last component that we looked into was, like I said, a little intercomparison between Snow 17 and iSnowball as a model. So the dashed lines here represent Snow 17 and the solid lines represent iSnowball. And we see a similar picture like we saw almost earlier in the spatial comparison, where we have the lower and the middle HRUs are these. So I should note that, like I showed earlier on the map. So the lower elevations and the middle elevation perform better if we look at kind of the build-up and the melt out, how SWE was available. It was only the higher elevations that again jumped out, where we had less SWE in iSnowball versus Snow 17. But that being said, we have here a modeling comparison, so none of the 2 are the truth as we know it. So to wrap it up and open up for questions soon here, takeaways were that the HYR forcing at the 3-kilometer grid size were pretty good. So we had good enough snow built up. The SWE matched better in the lower and the middle elevation compared to the higher ones. But iSnowball definitely needs an improvement when it comes to melt timing and also the different aspect timings there, or melt patterns. Our next steps that we want to take this project to is we're going to compare the net solar radiation. So this is one of our guesses right now that needs improvement to get this better melt timing and magnitude. This is also kind of conjunction with the next point, where we want to integrate remotely sensed observed albedo. So there we think also better melt timing comes with better albedo representation. And then last but not least, of course, this also needs to be tested in-house at the CBRC, because they in the end need to be ones that run the model on a day-to-day basis. All this work that I presented right here has been wrapped up and submitted to the geoscientific model development. So look out for an email from them soon, hopefully for discussion. And with that, I am all at the end. That's 4:30 and open for question.
Excellent. Thank you very much. Do we have any questions? Not seeing anything in chat. Vincent.
Thanks, Chris. Thanks, Joachim, for the very interesting presentation. I was wondering, you mentioned this, you tend to have an overestimation of snow depth compared to the ISO data at high elevation. Could you comment on the representation of processes that can explain like snow ablation at high altitude, such as sublimation or wind-induced snow redistribution? How is it represented in ice snowball? Thanks.
So I think I want to go one back also and going into the input of ice snowballs. So we think, for instance, that at the higher elevations with the precipitation, the mountains, at 3 kilometers are pretty flat. So I think there also we can't detrend the precipitation data enough, so to say, that we get more mass at the high and less at the bottom. So this is what ice snowball basically does. It takes the input from precip and tries to trend it based on elevation. And I think, this is one of the underlying reasons where we obviously can find that the high mountains have too little precipitation up high. And there's just kind of the starting point also where we're going to look at then, for instance, with the melt patterns, where we have kind of the net solar where we talked about. When we melt too little in the northern aspects, that means our ice snowball will still have too high in the northern aspects. And that's why it also jumps out in the spatial comparison where we saw there is something that needs to be improved, I think, also in both like input and then later on in the melt.
Okay, thanks.
Do you have any other questions? If not, we've got a few minutes here. I think perhaps we'll just open up the floor to questions for all of the speakers. And just see if there's anything that we've missed in the questions.
Can I ask a quick question?
Yes, of course.
Yes. Yes, for the comparison between this AUS SWE dataset and this ice snowball model output, I think you run the model at this 3 kilometer resolution, right? Am I correct?
So the model is running 50 meters, but the input
50.
from the HER is 3 kilometers.
Oh, okay. Okay, that makes more sense. So yeah, I think just misunderstand those things. So do you think is that result is kind of applicable for other mountainous areas? High elevation is continually is underestimate and low elevation is underestimate, or specific maybe specifically for this reason? Is there any other thought for that?
Yeah, so there you definitely bring it up here. So the East River that we picked has very sparse radar observations. So HER, of course, has a little harder time getting some real physical measurements into its spin-up time. So there we most rely on the physics. And we also do want to apply this to a bigger area to see what you just mentioned about how is the same bias like applicable to other areas. And we are currently doing that. So hold tight for maybe more results there. But I think the high elevations will still need some improvements. But yeah, definitely. There's two sides, right?
Right. Thank you.
Yeah, certainly my experience in the mountains is you're always at the mercy of the precipitation. Yeah.
Yeah, we wish we would have more, right?
yeah, exactly, right. It's if that input's wrong, it's just there's not much you can do about it. I was wondering what you're using for vegetation heights. And the interaction
we have a vegetation surface type. So we basically have a categorization, and then based off that, we have basic calibration parameters that will influence whether vegetation influences the melt pattern after that. So we don't have a vegetation height model per se in ice snowball.
Yeah, sounds good. All right. Well, we were kind of down to the minute here. If there's any other last question, open the floor. All right, excellent. Well, I would really like to thank all of our speakers, lots of really interesting conversations and presentations. I'd really like to thank our volunteer Aiden for kind of making the technology here all work. And yeah, I think that's all we've got for today. So thank you very much for attending. Thank you very much for the presentations, and we'll see you throughout the week. Have a good one.